In this question, a scientist is investigating a fictional reversible reaction involving fictional substances Q2, L2TG3, Q2TG3, and L4 at 962 Kelvin. So again, we've got that reversible reaction arrow there, showing our reaction can go both forwards and backwards. Our first step is writing an expression for the equilibrium constant, Kp, in terms of partial pressures for this reaction. So this is going to work exactly the same way as on our previous question. Here's our expression for equilibrium constant. So we have our products in the top of the fraction to the power of their coefficients. We have our reactants in the bottom of the fraction to the power of their coefficients. But because we're asked for Kp instead of K, instead of those concentrations in there, it's going to be the pressures. Only gases are included in the Kp equation. So let's go ahead and figure that out. For the top of our fraction, we've got our products. We've got Q2TG3, which is a gas, so that is going to appear in our equation, and the coefficient is 2, so it's going to be squared. So we've got the pressure of Q2TG3, and that's going to be squared. Our other product is L4, which is a gas, and the coefficient is just 1. So we're going to multiply that by the pressure of L4 to the power of 1. But remember, to the power of 1 is just the same as the thing itself. Then we're going to divide that by our reactants. We've got Q2, which is a gas, so that is going to appear in our equation, and the coefficient is 2, so it's going to be squared. So we've got the partial pressure of Q2 squared. We've then got L2TG3, which again is a gas, so it's going to appear in our equation. And we've got a 2 as our coefficient, so it's going to be squared. So that's multiplied by the pressure of L2TG3 squared. Awesome, so let's fill those into our answer boxes here. So we've got Q2TG3 squared times PL4, and we've got Q2 squared times L2TG3 squared. Next, we're told a scientist initially adds Q2 and L2TG3 to a previously empty container so that their partial pressures are as follows. The pressure of Q2 is 2.91 atm, and the pressure of L2TG3 is 2.85 atm. So let's go ahead and fill out those values in our ICE table down here. So for the pressure of Q2 at the beginning, it's 2.91. For the pressure of L2TG3 at the beginning, the pressure is 2.85. We're told it was added to a previously empty container. So the pressures of Q2TG3 and L4 are both going to be 0. We're also told that when the system reaches equilibrium, the total pressure in the container is 5.12 atm. So the sum of all of those equilibrium partial pressures is going to be 5.12 atm. Okay. Next step is to use our chemical equation to write an expression for the changes in the partial pressure of each substance. Since we're starting with our reactants and we've got 0 products to start with, we know that we're going to be decreasing our pressures of our reactants and increasing our pressures of our products. So I'm going to use negative 2 times x and negative 2 times x to show what our reactants are losing in terms of pressure. I'm going to use positive 2 times x and positive x to show what our products are gaining in terms of pressure. And remember, those 2's are coming from the fact that we've got a coefficient of 2 for those things in our equation. L4 has a coefficient of 1, so we've just got 1x there. So let's write those into our change in partial pressure row. We've got negative 2x, negative 2x, positive 2x, and positive x. Okay, now we don't have any columns where we know both the initial and equilibrium partial pressure. However, we do know the total pressure in the container at the end. So my next step is going to be writing an expression for my equilibrium partial pressure for each of my compounds so that I can use that together with the total pressure to figure out what x is. So here it's going to be 2.91 minus 2x, because we're taking our initial and we're adding our change. For L2TG3, it's going to be 2.85 minus 2x. For Q2TG3, it's going to be 0 plus 2x, which is just 2x. And for L4, it's going to be 0 plus x, which is just x. So if we add all those things together, we're going to get 5.12 atm as our total pressure according to Dalton's law. So let's write that all out. We've got 2.91 minus 2x plus 2.85 minus 2x plus 2x plus x is equal to 5.12. Okay, so we've got 2.91 plus 2.85 in terms of our numbers on the left-hand side. Then in terms of our x's, we've got negative 2x plus 2x plus x. So for our numbers, let's do 2.91 plus 2.85. That gets us 5.76. And then for our x's, we've got negative 2 and negative 2, which is negative 4x. And then we've got positive 2 and positive 1, which is positive 3x. So overall, minus 4x plus 3x gets us minus x. So that's 5.76 minus x is 5.12. Okay, so let's add x to both sides so that my x's will cancel on the left. I'm left with 5.76 is equal to 5.12 plus x. Finally, let's subtract 5.12 from both sides. That leaves me with x is equal to 5.76 minus 5.12, which gets me an x value of 0.64. Okay, so now we've found x. We're going to use that to figure out the change in partial pressure for each of our substances. So we've got negative 2x for the partial pressure of Q2, which is negative 2 times 0.64, which gets us negative 1.28. We also have negative 2x for the pressure of L2TG3. So again, that's going to be negative 2 times 0.64 for a change of negative 1.28. For Q2TG3, we've got positive 2x. So that's going to be positive 2 times 0.64, which gets us a change of 1.28. And finally, for L4, we've got positive x, which is positive 0.64, or in other words, just 0.64. So let's go ahead and fill those out in our change in partial pressure row in our table. So we've got negative 1.28 for Q2, negative 1.28 for L2G3, positive 1.28 for Q2TG3, and positive 0.64 for L4. Remember, we don't need a positive sign for positive numbers in our answer boxes, but we do need a negative sign before negative numbers. All right, we've got our changes in partial pressure. We've got our initial partial pressure. Now, all we need to do is add those together to get our equilibrium partial pressures. So let's do that now. So here we've got 2.91 minus 1.28. That gets 1.63 atm as our partial pressure. Then for L2TG3, we've got 2.85 minus 1.28. That gets us 1.57 atm as our partial pressure. For Q2TG3, our initial was 0, so 0 plus 1.28 is just 1.28. And the same for L4, our initial was 0, and 0 plus 0.64 is just 0.64. Awesome. So we found our equilibrium partial pressures. Let's just do a quick check to make sure that adds up to 5.12. So I'm going to put in my calculator 1.63 plus 1.57 plus 1.28 plus 0.64, and that gets me 5.12, which matches up with what we expected. Wonderful. So our last step is calculating the equilibrium constant Kp for this reaction at 962 Kelvin. So to do that, all we need to do is put our equilibrium partial pressure values into our Kp expression. So the partial pressure of Q2Tg3 at equilibrium is 1.28, and that's squared. The partial pressure of L4 at equilibrium is 0.64, divided by the partial pressure of Q2 at equilibrium, which is 1.63, and that's squared, multiplied by the partial pressure of L2Tg3 at equilibrium, which is 1.57, and that's also squared. So if we put that all into our calculator, that gets us an answer of 0.160 for Kp. So let's fill that in down here to check we got that right. Awesome. So this question works very similarly to the previous problem. The only difference is that instead of being given one of the equilibrium partial pressures, we're given the total pressure at equilibrium, which is the sum of the partial pressures of all the gases that are in our mixture. So you're going to have to write your expressions for the change in partial pressure, add those to your initial partial pressures to get expressions for your equilibrium partial pressure, and then add all those up to get your total which was provided, and solve that equation to figure out what x is.